Section A2, Part 1, Integration by Parts. Integration by parts is a technique for us for more advanced integration, and this time it'll be involving products. Now, the most common situation with products, of course, is that we're including transcendental functions. Remember, transcendental functions are those that are not polynomial, oftentimes like natural logarithms, trigonometric, things like that. So when we have a product of things that include that, obviously we can't do some basic algebra to just do the power rule. So we're stuck with it as a product. And to get rid of that and deal with it and find the antiderivative, we have this technique called parts. So to help us identify how we're going to do this, let's go back to the derivative of a product, okay, the product rule. So when you take the derivative of u with respect to x, that means it's going to be 1 times your second one, v, du dx, plus the derivative of v, which is 1 times u dv dx. Okay, so now that we have this in place, we can start moving things around and kind of make this work for us. So obviously, our next step is to look at it like it's an integral. So if we integrate this side with the dx, and then integrate all of this stuff here with the dx, let's simplify. Now over here on the right side, obviously, we're just going to have the integral of the derivative, right, of uv dx, okay? And then what I'm going to do is separate this. First off, I'm going to say that we have the integral of our u dv dx, and then I'm going to add on this one the antiderivative of v du dx with respect to x. Now, the first thing we should notice is that over here on the left side, antidifferentiating the derivative are absolutely inverse functions, right? They're going to undo one another. So over here on the left side, I'm just left with u times v. Now, on the right side, we have to kind of simplify these expressions. Clearly, in both of these, we can cancel out the dx parts, right? Those definitely go away. So what we're left with in the first one is literally just the integral of u dv, and then in this one is the integral of v du. Now, these are the things we're going to use to create the techniques of integration by parts. But what we want to do is solve for this piece here in the middle, because this is going to give us the options and the product we want to put things together. So what I'm going to do is solve for this right here. To do that, I'm going to take this part and subtract it over here to the left side. So when I do that, that tells me that the integral of u dv, okay, this right here, is equal to the uv minus the integral of v du. Now, it doesn't really feel like I did too much. Honestly, I just simplified the product rule, moved things around using integrals. But now what I've done is give myself a method, right? A setup, a viewpoint based on my product to get the answer. So what I know is that if I view what I'm given as a product between a u and a dv, I can do some things with them to fit this model. So what I'll do is basically take u times v, which I'll need to figure out, minus the integral of v to u. Okay, and again, we'll have to figure out v. So even just to use this whole like formula, we only have half the parts of them. We'll have to figure some things out. So there'll be a little bit of a setup, but again, this is going to help us understand how to antidifferentiate this sort of product. So integration by parts, like I said, is going to be looked at this way. We're going to take whatever we're given and view it as a u and a dv. The part that we consider the u, we're going to find the derivative of because we need du. Likewise, whatever the part that's the dv, we're going to find the antiderivative of it because we need v. So that's kind of some upfront work. Once we do that work, we just plug it into this expression right here, simplify it, which obviously will mean finding the antiderivative here, and that will give us our final result. Okay, that's what we're looking for. Now, obviously, the real important part of doing this is when you look at the original integrand, understanding what should be u and what should be dv. So some guidelines to help you make that decision are this. Whatever you want to be the dv, that's usually a little more complicated, but more importantly, it is something that you can antidifferentiate. So it's got to fit a basic rule. So obviously, whatever your choice of dv is, you're going to have to find this antiderivative to get v, so that's got to be something you can do. Now, the u, right, usually that's a more simplistic idea and one whose derivative kind of reduces it, oftentimes makes it go away. That's something that you want to think about because obviously with derivatives, especially maybe being the polynomial part, you can differentiate it away so it kind of disappears. It makes this a lot easier. Also, of course, you'll differentiate it because you need du. Now, one important thing to note, whatever you choose to be the dv, that will of course include the original dx in the integrand. So when you're looking at the original product, whatever your choice of u is can be it, and then whatever your choice of dv is will be, that part of it with the dx that's already sitting there. So let's draw a real basic example so you can kind of see the process. So what I'm going to do is identify my u and my dv, okay, and then once I have that, I'm going to find all the rest of the pieces that I need. So as a reminder, okay, whatever I choose for my u and my dv, that product, right, is going to equal to u times v minus the integral of v du. And I like to remind ourselves of these pieces because obviously as we do this, we need all of these things. I only have u and dv, so we're going to figure out the other two. So the way I like to organize my thoughts is this, okay? Just like in substitution, we'll identify what our u is going to be. Well, between e to the x and x is the more simplistic version, and its derivative does kind of make it go away. So that's a really good choice for u. So u is going to equal x. Now, the other part we have to figure out, of course, is dv. Now, I actually kind of write it down here, and I do that just because on my top line, I kind of look at those as like equations and then their derivatives below, but you can organize it however you want. This is just what I do. But again, the rest of it is going to be this way. Now, one of the reasons I'd like to do that is when we do integration by parts, we have to both find derivatives and antiderivatives at the same time. So it's very important you go slow and make sure your mind's in the right place just so you don't accidentally, apply the power rule wrong. Okay, so be really careful on going back and forth. That's another reason I write them this way. When I write something below, I'm differentiating. When I write something above, I'm kind of working backwards in my mind, so I think of that when I do my antidifferentiation. So the derivative of u, du, is going to equal 1. Okay, so there's that. And of course, as you do that, that's really just 1 times dx. So I'll just write dx there. And then to find v, we'll just find the integral of e to the x. Okay, and the antiderivative of e to the x is simply e to the x. Now, if you'll notice, I did not write the plus c, and we don't do that because, to be honest, if you did include it, and then you plugged in all this stuff and worked it out, it would actually go away anyway and cancel out. So I'm just going to tell you right now, in this setup part where you're identifying the v, you do not need your plus c. Okay, and you can see that in my work if you go back and redo this example with a plus c in there. I promise it cancels out. Okay, so I identify my u and my dv. I differentiated. I antidifferentiated, so now I have all the pieces I need. So I'm going to take u times v, right? So that's going to be the first part here, and then subtract from that the integral of v with my du. The only piece of these 4 things you don't use is actually right here, okay? Because the only thing this helped us was to identify v. When we actually use the formula, we just need the u times the v, and then minus the integral of the v, this stuff here, with du, which will be our dx. Okay, so let's use our formula. Okay, so the antiderivative here is going to equal our u times our v minus the integral of our v du, which is, again, dx. Now, we know this is going to work because this is an antiderivative I can find. Okay, we can actually work that out. But really, it's just a matter of just plugging into the formula. Okay, we took our whatever our u is, whatever our v is, multiply them together, minus whatever our v is in du in the integral. So if we go ahead and work this out, this part obviously is just going to be x times e to the x. The antiderivative of e to the x again will just be that. And here is where you have your plus c. Let's try another example, this time with x and cosine x. Now, for the same reason, I think u being x is a great choice. Again, cosine x is something I can easily antidifferentiate. It's not really going to go away or anything, so that will be my dv. So just like before, we're going to say that my u is going to equal at x. Okay, so that means du equals dx. Now, my dv is the rest of it. It is the cosine of x dx, whose antiderivative, right, will give us v. So what did we take the derivative of to get the cosine of x? Well, that would be the sine of x. And again, we do not need the plus c. So now using these pieces, we'll fit that into the integration by parts formula. So that means this right here equals the u times our v, okay, so x times sine of x, minus the integral of our v, which is sine of x du. And again, this works out because I definitely know the antiderivative of the sine of x. So this whole thing works out to be x times the sine of x plus the cosine of x plus c. And again, the sign change happens because the antiderivative of the sine of x is negative cosine of x. And along with this minus here, that's going to give us a plus sign. Now, in this example, this is kind of a special case. Now, the reason I bring up this special case is because, and we've talked about this before, anytime you have an integrand and inside your integrand you have a natural logarithm, that must be the choice that you make for u, okay? Natural logarithms are only differentiated, they're not antidifferentiated, okay? So it's important that when we do this, we make that choice. So here, even though it's very tempting to say we could do x, it must be the natural log of x, all right? So that means its derivative will be 1 over x dx. Okay, so the rest of it must be my dv. Now the rest of it is an x and a dx, and now to find v, we'll antidifferentiate that, so that'll be 1/2 x squared. So now that I have those pieces together, let's put that into the formula for parts. So it's our u times our v, so I like to write it this way. I like to write the natural logarithm last. Okay, there's u times v minus the integral of our v, which is 1/2 x squared, times our du, so 1 over x dx. Now in this example, we probably want to go ahead and simplify it, right? In order to make this an easier antiderivative, let's combine some terms and make it look a little bit nicer. So that means we're still going to have the 1/2 x squared natural log of x, that's the product of u and v, but I'm going to throw the 1/2 out front, and if you take x squared times 1 over x, that's just x. All right, so let's get to our answer. So again, one more time, copying down our u times v. Now the antiderivative of x is going to be the 1/2 x squared. So when you put that together with 1/2 on the outside, it becomes 1/4 x squared plus c. Now, in our first three examples, real quick, we'll notice that we basically just found our pieces, put them together, and got the answer. But there are cases like this where you might need to use the idea of parts multiple times. Oftentimes this will come up when you have something that is a pretty obvious choice for u, but it might be raised to a power. So instead of looking at our original example where we had x to the first and doing one derivative kind of made it go away, in this example, it's going to take two derivatives to make that go away. It's not a big deal, but you want to be very careful since we're going to do this more than one time that we use good grouping symbols to make the correct signs work as we go through. So just like our last example, the u here is obviously going to be x squared, okay? So that means du is going to be 2x dx. The rest of it is going to be my dv. So the rest of it, just like our first example, is e to the x dx, whose antiderivative gives us v, which will be e to the x. Now what you'll notice is when we plug this in the formula, we're not done, right? In the formula, we're going to get another integral that requires parts, okay? So if I put this together, we're going to have u times v, so x squared e to the x, minus the integral of our v, which is e to the x, times the rest of this here, 2x dx. So what we notice here is this right here is not an easy antiderivative like our first couple examples. We're going to need to use parts on this again. But keep in mind, we already have this part in front. We're subtracting the parts here. So we need to make sure we're very careful when we use the grouping, okay? So before we do that, I'm going to clean this up a little bit. So I'm going to call this x squared e to the x minus 2 times the integral of x e to the x dx, okay? So what's going to happen is one more time, will do parts just on this part. And when I put that formula for parts together, I'm going to put it in brackets because technically we'll be multiplying our -2 times all of that. Now in this case, again, doing it again, the u again will be x, whose derivative will just be a 1 dx. The rest of it, again, is going to be e to the x dx. And what you want to notice is my choices of u and v mimic exactly what I did the first time through. Whatever you kind of choose for your u's and v's, that's going to be the same thing you do each time. You don't really switch, you stick with it. So since my dv was e to the x, we're going to stick with that. And again, the v will be the same thing, just e to the x. Okay, so now when I put all this together, here's how it's going to look, okay? So first off, you're going to copy all of this. We have the the x squared e to the x minus 2. So we have our x squared e to the x minus 2, but we're now going to replace this integral here with the formula for parts using these u's and v's. So that means I'm going to take u times v from the green here, so this will be x times e to the x, minus the integral of v du, so this will be e to the x dx. And I know that I'm not going to need to do it again because now, unlike what happened up here, this is a pretty obvious, easy antiderivative. But keep in mind, when we do this, right, we'll find the antiderivative, but this -2 goes to each one of those. And again, that's very important because the formula for parts has a subtraction in it, but technically, we are multiplying -2 times all of it. That's why I want those brackets there to get the correct plus sign that should happen right here. So the final answer, again, is going to be the x squared e to the x minus 2x e to the x when I distribute to the first one. And then when I distribute this here, it's going to be negative 2 times negative 1, right, times the antiderivative, which is just e to the x plus c. Now, there could be situations where perhaps this whole method, we might actually do more than twice. In fact, looking at this example here, now we have x to the cube times sine of x. So you might say to yourself, it might take 3 derivatives to make this go away, and that's true. Now, the good news is we don't need to keep doing this layout because, if we did this more than 2 or 3 times, this gets very cumbersome. Instead, there's a lot of repetition in the algorithm, and so there's a method called the tabular method that helps us organize our thoughts to repeatedly use integration by parts, okay? So if you look at the table I set up here, these are the pieces you need. The first column is going to have our pluses and minuses. The middle column will talk about u's. Now, it's important to remember, whatever you choose to be your u's, this is the stuff that you're going to be differentiating, okay? So just make sure that this list are derivatives. Likewise, our last column, dv's, these are things that we're going to anti-differentiate. So again, as we work through something like this, it's very important as we go through it that we put anti-derivatives going forward. Again, like any problem involving parts, your mind is going both directions, right? You're doing derivatives, you're doing anti-derivatives. You want to make sure you keep it very straight in your mind, okay? So be careful as we do this. So here's how it works. First off, you want to go ahead and pick the signs, right? Obviously, for each one. You always begin with positive and then you alternate. And that makes sense because looking back at this example, we have plus minus, but then when we distribute, we get a sign change. So as we go through and do this kind of tabular method, what we're going to do is say that we start with a plus sign and then do a minus sign and a plus and so on. Now, if you're wondering how far down do we need to go, well, actually, that's determined by the u. So sometimes I'll actually fill out the middle part of the table first, because when this middle part gets to 0, that's when you stop. That will tell you how far down these things need to go. So I'm going to erase this, and I'm actually going to start here in the middle to give me an idea how far I need to go down with my pluses or minuses. Now in this example, again, the u is obviously going to be my x to the third because I can differentiate it away. Sine of x ain't going anywhere, but it is an easy antiderivative, so that'll be my dv. All right, so that means I'm going to start with my u value being x raised to the third. So to determine how long and this table is going to go in all the columns, we take this right here and now differentiate it away. So the derivative here is going to be 3x squared. Its derivative will be 6x. Its derivative will be 6. And then finally, we get all the way down to 0. And that tells me how far to go. So in my first column, we have a plus, a minus, a plus, a minus, and a plus. Now in the last column, again, we're going to have our dv, right? And I'm just going to write sine of x here. I know there should be the dx with it, but we're just listing the terms that we're going to put together. So I'm just going to write down the dv part of it and just find antiderivatives. Okay, so again, the common mistake is after differentiating down, now we must anti-differentiate. So we're going to be very careful we do it correctly. So again, asking ourselves, what do we take the derivative of to get sine? Well, that's going to be negative cosine x. Okay, what do we take the derivative of to get negative cosine? Well, working backwards, that would give us negative sine. And cosine would be the antiderivative of that, since cosine's derivative is negative sine. And again, sine would be the last one I need. Now, once you've filled those out, what you can do is this. Okay, we listed our derivatives stopping at 0. We listed all of our antiderivatives. So the solution is going to be this. We're going to add up all of the signed products of the diagonal entries. Okay, so let me kind of illustrate what this looks like. You're basically going to start here with this sign. So it's going to be positive x cubed times negative cosine x plus negative 3x squared times negative sine of x plus positive 6x times cosine of x plus negative 6 times sine of x. Okay, so as you can see, we have some diagonals. The diagonals between u and dv. The signs kind of go with it. So I, in my mind, kind of put these two parts together, positive, negative, and so on, and then you go diagonally down and multiply. And then you just take all those terms and add them together. And don't forget, obviously, at the end, do a plus c, because this right here does produce the antiderivative overall of the product. So in this case, our answer is going to be positive x cubed times negative cosine of x, which would be negative x cubed cosine of x when you simplify it. Okay. The next term is going to be negative 3x squared times negative sine of x. Well, the negatives make it positive, so that means it's going to be plus 3x squared sine of x. Okay, the next term is going to be a positive 6x times a cosine of x. Okay, so it'll be positive 6x times cosine of x. And then the last term is going to be a negative 6 times the sine of x. So that means it's going to be negative 6 sine of x. And as always, don't forget to write your plus c. Okay, let's try it one more time, except we're going to use x to the fourth times e to the negative 2x. Now again, in this case, should I do it just manually, it probably would take 4 times through, which again becomes very cumbersome. The tabular method is a lot nicer. So just like before, I think x to the fourth, something I can differentiate away. Clear and easy choice of u, which means e to the negative 2x, that's going to be my dv. So in this problem, we're going to go ahead and say x to the fourth, and let's go ahead and find its derivative so we can figure out how big this table is going to be. So we're going to have 4x to the third, 12x squared, 24x, 24, and then 0. Okay, so that's going to get me all the way to where I need to go. Now, the next thing, obviously, is do our pluses and minuses. So we got a plus, a minus, a plus, a minus, a plus, and a minus. Okay. Now, if you haven't noticed, you actually don't end up using this one, but, you know, it's good to have the pattern. Likewise, you don't actually end up using this one. These parts of the table, you don't really get to use since you're kind of going diagonally, but you definitely want to fill them out. So dv is e to the negative 2x. Now, we got to be really careful here when we find our antiderivatives. We want to make sure as we do this, we get the right piece in the right place. All right, so when we talk about the antiderivative of e to the negative 2x, technically that would be like a substitution idea with u being the negative 2x. So when you find this antiderivative, it works out to be negative 1/2 e to the negative 2x. Basically, you're going to multiply by negative 1/2 each time. So if I do it again, it becomes positive 1/4 e to the negative 2x, and then negative 1/8 e to the negative 2x, then positive 1/16 e to the negative 2x, and lastly, it'll be negative 1/32 e to the negative 2x. Because again, every time you're anti-differentiating, you have that extra negative 1/2 in front by substitution. So if that's something you need to work on at the side of your paper, that's fine. A check that I like to think of is, you know, the derivative of e to the negative 2x is just negative 2 times e to the negative 2x. So I just want that reciprocal to kind of make it go away. Okay, so let's focus on our diagonals. Here it's going to be positive x to the fourth times this, negative 4x to the third times this, and then these two, and these two. Now again, we're going to pay close attention to when we have sign changes. Here's a positive times a negative. This is negative times positive times negative, negative times positive, and positive times negative. So we have to be really careful that we get the correct sign. All right, so here we go. The answer is going to be, again, positive 4x times negative 1/3. 1/2 e to the negative 2x. So if I put that together nicely, we have a negative 1/2, we have an x to the fourth, and an e to the negative 2x. Okay, so there's our first term. Now, in our next one, okay, as you can see, we're going to have a negative times a positive, so it's going to be negative there. And the 4 and the 1/4 actually cancel, so that's just going to give me x to the third, e to the negative 2x. In our third term, we're going to have positive times negative, so this will be a minus, and we're going to take 12 over 8, which I suppose if you want to, you can leave it. However, I'm going to reduce that because the 4 goes into both of them, so it'll be negative 3/2 x squared e to the negative 2x. And then in our next one, now we have a negative 24x times the positive here. So again, that's going to be another negative term. And if you take 24/16, that's basically going to be, when you take a 4 out of those, 6/4, I suppose. So we can actually take an 8 out of it, so we have 3/2. So we'll call that 3/2 x and then e to the negative 2x. And I got one more term here, so it'll be a positive 24 times this right here. So that means it'll be, again, another negative. 24/32 will be, let's see what goes into both those. 8 goes into both of those, so it'll be what, 3/4? Be negative. And then again, x to the negative 2x. And of course, as always, do not forget your plus c.